Hello, my name is David Lee, and I'm with Virginia Asphalt Association, and today we're going to talk to you about the blending of aggregates for mix design. And we'll speak about a number of things associated with mix design today, but keep in mind that the bulk of this presentation is specifically talking about blending of aggregates. So let's quickly go over the objectives for the presentation. So on the completion of the module, you should be able to describe the components of a basic job mix formula. You should be able to describe the process of blending aggregates for mix design, and then be able to combine aggregates to achieve the target blend using what's called basically a trial and error method and appropriate blending worksheets that are associated with that trial and error method. And then lastly, we're going to briefly go over how to calculate cold feed blends. So before I get into the actual blending of the aggregates, let's talk for a minute about mix design and specifically about the job mix formula. Well, asphalt mixes are a very complex mixture in reality. The basics tell you that they are a combination of aggregates and liquid asphalt, and that is a very true statement. However, you have to take all of those ingredients together to produce a mix that meets all the requirements to be placed on a typical roadway surface. You need that mix to be durable, you need that mix to be crack resistant, and you need it to last a long time so that we don't have to get back out in the roadway very quickly. So to do that, we take a blend of different aggregates together, and we try to meet a specified target for the various mixes. Surface mixes have a specific target that are being used. We have intermediate type mixes, and we have base mixes that we'll get into further when we talk to you about some of the specific requirements for each type. Well, a mix designer can manipulate basically three variables, and those three variables are the aggregate, which we're going to spend the most time on today, the asphalt binder itself, or the liquid asphalt that's used into that mixture, and the ratio of those two together, the ratio of the asphalt binder to the aggregate itself. That's the basics of an overall mix design process, and those are the three variables that can be manipulated. And we're going to particularly talk about the one of the blending of aggregates today. Now I'm going to ask you to refer to your road and bridge specifications for VDOT, which is what this presentation is based around, and specifically about section 211 for asphalt concrete, which has table 213 and section 211.03 for the various mixes that are used. So when we talk about a job mix formula, those are basically two components that ultimately combine to make a job mix formula. We do a combination of the aggregates, and there's different gradations that are used that combine together to create an aggregate skeleton. Then we add the asphalt cement itself, or at a specific asphalt content, and that will ultimately produce a specific job mix formula. All of these are necessary to meet the specific specification requirements that I just referred to in section 211. So real quickly, the steps that are associated with the overall mix design process are on this slide, and you'll see that you get to select the aggregate. So you have to evaluate and select the specific aggregate. Ultimately, you'll also do that for the binder and their sources. And the aggregates, today we're going to talk specifically about the gradation requirements, but the aggregates must meet physical tests for each of those sources. They have to meet a soundness requirement as well as an LA abrasion to determine their freeze-thaw susceptibility as well as their durability. We're going to select the specific asphalt binder. Each mix requires a specific type of asphalt binder to be in that mix. For example, a 12.5A surface mix may require a different binder than a base mix that will use for like a BM25. And then ultimately, in the mix design process, you'll determine the optimum mix content. That is, you'll take several trial and error mixes, you'll compact those in a laboratory to simulate field conditions, and then you'll run tests to determine that they meet all the key characteristics that are part of the specification requirements. But today we're going to specifically talk to you about the blending of aggregates. So if you go to that table that I referred to earlier, which is table 213 in section 211 of the road and bridge specifications, you'll see the design gradations for various types of mixtures. And for the purposes of this presentation, we've narrowed that down to the mixes that you see on the slide. You'll see a surface mix, an SM 9.0, an SM 9.5, and an SM 12.5. All of those are specific surface mixes. Then you have the intermediate mix, an IM 19.0, You have a base mix of BM25, and then you even have something called a curb mix, which we're not going to go into today. So, the trial and error method for combining aggregates. This is what we're going to spend most of our time on today. And the first step is you have to obtain and enter the required data for a blending worksheet. And by that I mean what you're going to do is you're going to go out and you're going to get all the samples for the specific aggregates that are going to be used for the mix that you're producing. On step 2, you're going to enter specific target values for the mix that you're trying to produce. And then on step 3, you'll estimate the proportions to get the combination of the gradation that you specifically need. And then you're going to calculate in step 4, calculate the individual proportions and combine gradation to achieve the total blend for that specific mixture. Then ultimately you go back to that chart that I spoke to earlier, table 213 for the design requirements, and you compare your total blend to those target values. So let's go through a sample problem real quickly. So our first sample here, we have a blend of aggregates that have both a fine aggregate and a coarse aggregate. So this is a 2 aggregate blend of asphalt that we're trying to produce, and ultimately this is a 12.5A, an SM 12.5A mixture. We've gone to our stockpiles and we've pulled samples to run gradations on those samples, and you see the data in the chart for the percent passing for the fine aggregate, and you see also the data for the coarse aggregate and the percent passing for both of those specific aggregates. Then lastly, you'll see on the last column that design range that I spoke to. That came off of that same table, section 213, and it's out of section 211 of the road and bridge specifications. We got the gradations for each of those 2 aggregates that are used for your asphalt combination. So as I said a minute ago, you got to go back to table 213. Table 213 has the SM 12.5A blend requirements for the design ranges. You take those and you pull those off of that table and you put them back into that table that I showed you just a minute ago, and you start to set your target values. So these target values are going to come from your mix designer. They typically come from experience. There's somebody that's obviously worked in this field and they have determined where they typically would be based on the aggregates they're using. So the design range for, say, the number 4 sieve is 58 to 80, and in this specific case, we're going to set a target value of 74. And on the 30 sieve, you have a maximum of 23 allowed for the design range, and we're going to set our target for 21. And then we'll go back and we'll actually fill in the same target values for each one of those sieves for this type of mix. So we have 100% passing the 3/4. We have 98 target on the half, a 88 target on the 3/8. As I said, a 74 target on the number 4, a 47 on the number 8, and a 21 on the number 30. Then lastly, you'll see on the number 200 sieve, the fine sieve, a target of 6, and our design range is from 2 to 10. So now we have our targets set for each one of those specific sieves for this mix type. So for a trial blend, we're going to start with something that we think is a possibility, and we're going to say, all right, let's just pick 50% of each one of these. So we have 50% of our blend is going to be fine aggregate, and 50% of our blend is going to be the coarse aggregate. So now we're going to go through and we're going to produce the blend, the percent blend column for each one of those aggregates based on that 50-50 split of those 2 aggregates. So if you take that data that we just came up with and you decide you want to plot that on the 45 power curve, you'll see that you have a lower value that is the red line, that is a coarse aggregate. You have an upper blue line, which is the fine aggregate. Those are the 2 dotted lines you see on the slide. Then you have what is your target value in that upper portion above the 45 power curve. So you can plot these on a 45 power curve so that as you go through this, you'll be able to determine how close you are to your actual targets based on our 45 power curve. One thing I want you to keep in mind as we go through this process, because we'll do this multiple times throughout this presentation, is that when finding the percent blend and the total blend, we have to remember that this has to be converted into a decimal. So we're converting our percentage of aggregate to a decimal by dividing by 100. So if we have 75%, let's say, as an example, of a specific aggregate type, we need to take 75 divided by 100 to create a multiplier decimal, which is 0.75. And then ultimately we'll take that combined gradation and get a total blend, which is the percent of the first aggregate plus the percent of the second aggregate to get your total blend. So let's continue on through this sample problem that we've started. Okay, so step 4 is to calculate the individual proportions. So as I said a minute ago, we have a 50-50 blend of our fine aggregate and our coarse aggregate. And if you go down this chart, you'll see if you take obviously 100% passing the 3/4 sieve and you multiply it by our multiplying factor of 50% or 0.5, we get 50% of our blend on the 3/4 sieve for the fine aggregate. We had 100% passing on the 3/4 sieve for the coarse aggregate, so we also have a 50% blend on the coarse aggregate. If you skip down to, let's say, the 3/8" sieve, you'll see that we had 94% passing the 3/8 sieve for the fine aggregate. You multiply that by 0.5, and you'll see you get 47. Moving over to the coarse aggregate on the 3/8" sieve, you see a 65% passing the 3/8" sieve, and you multiply that by 0.5, and you now get 32.5% of the blend is on that coarse aggregate. Let's skip down to the last one on the number 200 sieve, and you'll see you have 7.1% passing the number 200 sieve for the fine aggregate. Again, you multiply that by the same 0.5, and you get 3.6% of the blend is fine aggregate. You take the fact that we had 1.2% passing the number 200 sieve for the coarse aggregate, you multiply that by 0.5, and you'll see that you get 0.6% of the blend for this specific mix is on the coarse aggregate. So now, all we have to do is take each one of those two aggregates and add those two columns together. So we take our percent blend column for the fine aggregate, we take our percent blend column for the coarse aggregate, and we total those together to get the total blend, the column that you see in red. And you take each one of those and just add them together. Just simply add them together. So on the 3/4" sieve, you take your 50% blend on the fine aggregate and 50% blend on your coarse aggregate, and you get 100% on the total blend. Skipping down again to the 3/8" sieve, we had 47% of the blend on the 3/8" sieve was the fine aggregate, and we had 32.5% of the blend on the coarse aggregate. We add those two together and we get a total blend of 80. So one thing to keep in mind for all of these sieves is that you have to round these upper sieves to the nearest whole number. So everything with the exception of the number 200 sieve is rounded to a whole number. So let's go down to that number 200 sieve now. You'll see that you have on the 200 sieve, we had 3.6% of the blend on the fine aggregate. We had 0.6 of the blend on the coarse aggregate. You add those two numbers together and you get 4.2% total of the blend for this mix. And on the number 200 sieve, you carry that to the first decimal place. So you go to one decimal place, so it's 4.2 in this specific case. Now earlier we gave you the column for the target values for this specific mix. Now you just take that total blend and you compare that to the target value that you gave earlier, and you go down the line. And you see on the first one, where your target was 100, well, we got 100 on the 3/4" sieve. The next one was very close as well. The 1/2" sieve, our target was 97, and our total blend was 97, and our target value was 98. Skipping on down to, say, the number 4 sieve, you see that their total blend was 64, but our target was 74, so we weren't very close in that case. The next one, the number 8, we weren't very close on that one either. We had a target of 47 and we only achieved a 40. And then when you skip down to the number 200, our target was 6 and we were only at 4.2. So our blend of 50-50 didn't quite produce exactly what we were looking for from a target perspective. So now your question is, what do you do about that? Well, the next thing we need to do is take each one of these sieves, and we recognize that, say, on the 3/8" sieve, we had a total blend of 80 when our target value was 88. So we take that and we plot that on the 45 power curve that we had just a minute ago, and you see that our target line is well above what our 50-50 blend line was able to produce. We're looking for a line that would almost fall right on top of that target value line. So we need to make an adjustment. So how do we do that? How are we going to make this adjustment? Well, let's pick just one sieve. We don't need to do all of them at one time. In fact, we wouldn't be able to actually make the adjustment we need. Let's pick the 3/8" sieve, and that's the one where we had a total blend of 80 with a target value of 88, and we're going to make our adjustment based off of this 3/8" sieve. And we're going to go through this mathematically and just run a series of trials for this specific sieve at varying percentages. So our first one that we just ran a minute ago, if you recall, was a 50-50 blend. Our second trial would be, let's say, a 55 fine aggregate, 45 coarse aggregate. And we run a series of trials all the way down to our seventh trial will be a 40% fine aggregate and a 60% coarse aggregate. And then we essentially do the same thing we did earlier, but we're just doing it on the 3/8" sieve now. And we take 0.55 for that fine aggregate, we multiply it by the percent passing for that sieve, and that was 94, and now we get a 51.7. We carry that across and we do the same thing for our coarse aggregate. We had 45% there, so we do 0.45 times 65, and we now get 29.3. We total those two together and we get a total blend of 81. As you can see, we're still off of our target of 88. So let's skip down to the next trial. We have 60% on the fine aggregate. We take 0.6, we multiply that by 94. We now have a percent blend for the fine aggregate of 56.4. We carry that across and do the same thing for the coarse aggregate. We get 0.4 times 65% passing for that specific sieve, and we get 26 on the blend. So now we get a total blend of 82. So now again, our target is 88, so we're still a good ways off. Well, if we run that through on all of our trials, you'll start to see that each one of those was going to produce a number specifically for the blend and the total blend that you can compare against the job mix formula. And if we look closely, you'll see on trial number 5 that we had a total blend of 87 for this 3/8" sieve with our target being 88. So we're very close to the target for this one. So now we seem to have a pretty good place to make our adjustment to use a fine aggregate percentage of 75 and a coarse aggregate percentage of 25. So all we do is we go back into that original blend sheet and we rerun that blend sheet, now using fine aggregate percentage being at 75% and a coarse aggregate percentage being 25%. We run that through each and every sieve that we have before you, and we'll see that, and we'll be able to compare our target values to our design ranges. So now if you look at our target values compared to our total blends for this specific worksheet, you'll see that we had, for example, on the 1/2" sieve, we had 99 on the total blend. Our target was 98, so we're really very close. If you look on down to the number 4 sieve, we'll see that our total blend was 73, our target was 74, and all the way down to the number 200 sieve, our total blend was 5.6, and our target was 6. So with a blend of 75% fine aggregate and 25% coarse aggregate, we were able to achieve the target values, or very close to those target values, for this specific blend. Again, if you take that 45 power curve that I spoke to just a minute ago, you'll see that now our target value curve is on top of, or very close to, our 75-25 blend. So we now have achieved a blend that matches very closely to our target values. So now, let's look through another sample problem. So what if you need to use more than more than 2 aggregates? So let's say that we need to use 3 aggregates in this case, and let's try an intermediate mix, say an IM19A. So again, you've got all the same steps that we've had before, but now you'll see that we actually have 3 aggregates as opposed to 2. In this case, we're going to have a mineral filler, which is a very fine aggregate. We'll have our typical fine aggregate, and we'll have a coarse aggregate. And we have to do the same thing as we did before. We have to insert the design range and everything else for each one of these mixes. In this case, again, we're talking about an intermediate mix, an IM19A. We go back to that chart that we talked about before, table 213, that's in section 211 of the Road and Bridge specifications. and we pull those ranges right off of that chart. And you'll see they get inserted into the design range there at the end. If you recall, we had the same thing previously with our two aggregates. You actually have to have a gradation for the materials that you're using, whether those come from a stockpile that you have at your asphalt plant or they come from the quarry where you're going to be getting your aggregates from. You get a sample that's representative of that material for what you're going to be running on a day-to-day basis, and you actually insert those values into the percent passing for each one of those. So in this instance, we're going to do a trial and error for 40, 30, and 30. So we have 40% of mineral filler, we have 30% of fine aggregate, and we have 30% of a coarse aggregate. Again, we have to remember to put our design range in the end, and we have a target value that's set for each one of those sieves. If you see those target values, obviously must fall within the design range that was provided by Table 213. So now, it's the same process as we had with the two aggregate system. Now we're doing the three aggregates, so you just have to do it one extra time. So now we'll go down for the mineral filler. You'll see that we had 100% passing all of the sieves with the exception of the number 200 sieve. You multiply those by 0.4, and now you get 40% of the blend for each one of those sieves with the exception of the number 200 sieve, which had 28% passing. Multiply that by 0.4, and you get 11.2. We do that across the line for each one of the materials that you're using. In this case, we're going to go over to the fine aggregate. We had 100% passing the 1-inch sieve. You multiply that by 0.3, and you obviously get 30% of the blend is a fine aggregate. You skip down to, say, the half-inch sieve. We had 99% passing the half-inch sieve for that fine aggregate. Multiply that by 0.3, and you get 29.7. Go on down to the number 8 sieve. We had 69% passing for the fine aggregate, multiplied by 0.3, and you get 20.7. So we filled each one of those out. We can do the same thing, obviously, or we'll do the same thing for the coarse aggregate. And we take each one of those, and for example, let's look at the half-inch sieve again, and we had 47% passing the half-inch sieve. You multiplied that by 0.3, and you got 14.1. In this case, from a mathematical blending perspective, it made it pretty easy for the number 200 sieve because we had 0% passing for both the fine aggregate and the coarse aggregate. So both of those were zeros. So now, let's look at the blends for each one of those. So if you take each one of those and you fill in the percent blends like we just did, and you take those numbers and you total them like we did on the first example where we only had two aggregates, it's just a 3 aggregate system now, and you're doing exactly the same thing as we did before. So you take, let's say for the 1-inch sieve, you take the 40% blend for the mineral filler and the 30% of the blend for the fine aggregate and the 30% of the blend for the coarse aggregate, and you total those together and you get 100% of the total blend. Skipping on down to the half-inch sieve, and we total all those together, you total of 40 plus 29.7 plus 14.1, you total those together and you get 84. Again, keep in mind that the upper sieves, all with the exception of the number 200 sieve, are rounded to a whole number. For the number 200 sieve, in this case, again, we only had one sieve that had material on the 200 sieve, and that was the mineral filler. So you take 11.2, we had 0 on both the fine and the coarse aggregate, so we get an 11.2 for the total blend. Now, just as we did before, we're going to compare those to our target values. If you look at those upper 3 sieves, we had 100% target value for the 1-inch, and we met that requirement dead on at 100%. If you take the 3/4 inch sieve, our target was 98, we got 99. But then you look at the half-inch sieve, you'll see that our target was 79 and we got an 84. So we're a good ways off on that one. Same thing on the number 8, our target was 47 and we're at 63. And even on the 200 sieve, we're off with a target of 4.5 and we're at 11.2. So we have to do something to compare each one of those sieves and figure out which one we want to adjust based on. So we look at all those various blends and we look at our trials. We go back to a various series of trials just like we did before. We're not trying to do anything different than we did before, but we have to run a series of trials. In this case, we ran 5 different trials. You'll see that Each one of those trials produced a different blend for each one of those. But if you pick trial number 4, you'll see that with a mineral filler percentage of 20, a fine aggregate of 35, and a coarse aggregate of 45 for this trial, we were able to produce a total blend on the number 8 sieve that has a 48 compared to our target value of 47. If you go up and look at, say, trial number 2, you'll see that the total blend was 57 versus 47, and that one was way off. So at this stage of the game, let's look at trial number 4 and see if that one will actually produce a mix that meets our requirements. So we do the same thing as we did before. We take each and every one of those sieves and we combine them together now based off of the revised blend of 20% mineral filler, 35% fine aggregate, and 45% coarse aggregate. We rerun all those calculations for each one of those sieves and we come up with a total blend for this blend of materials. And you'll see now that if you look at each one of those sieves over there, like on the 3/4 inch sieve, we have 98 as a total blend. Our target was 98, so we're right on. For the number 8, just like we just said, we had a target of 47. We have a total blend of 48. However, you'll see now that on the number 200 sieve, while we're a whole lot closer, we're still a little ways off. Our target value was 4.5, but our total blend achieved something a little bit greater than that at 5.6. So we need to see if we can find a way to fix that. So now let's try to see if we can look at another adjustment. So let's adjust it based off that 200 sieve. So if we look at this 200 sieve and our target being 4.5, a minute ago we were able to look at some various blends. If we looked at a 10% mineral filler blend, we'll see that we had 28% again passing the number 200 sieve. We multiply that by 0.1, we get 2.8. Well, obviously we're way short of the 4.5, so that's not going to work. If we skip down to the bottom, if we tried 15% for our mineral filler, and we multiply that by the 0.15 times 28, and we'll see that we're right on 4.2, which was very close to our target of 4.5. So right now we know that our mineral filler needs to be set at 15%. So if we go back in and rerun those calculations one more time, we'll see that we're able to now produce, based on a blend of 15% mineral filler, 40% fine aggregate, and 45% coarse aggregate, we're able to produce a total blend that now comes very close to our specific target values. Don't forget to recalculate every single one of those blend values for that total blend of 15, 40, and 45 in this case. You'll see now that we're able to match our target values very closely. So for example, on the 1/2 inch sieve, we had a total blend of 76 with a target of 79. And as I said just a minute ago, on the number 200 sieve, we had a target value of 4.5 and we're at 4.2. So we were able to make an adjustment that now meets our total requirements for this specific mix, and this being an IM19A. So now let's walk through a study problem associated with cold feed blending. Keep in mind that the process that I've described so far is for mix design when you're actually creating a new mix for a specific type of mix, whether it be a surface mix or an intermediate, like I said. But this same process can also be used for determining cold feed blending at a plant. So let's walk through a sample problem for cold feed blending. So now, you have essentially the exact same thing as you had before. You've gone out to your stockpiles, you have run specific gradation tests on each of your materials. In this case, we have a screenings and what's just being called generally a stone. You're taking those two materials, you're doing a gradation on each one of those, and you're inserting it into this very similar or same blending worksheet. And you also have, in this case, you already have your target values from your mix design. So you insert those and put those in the next to the last column, and you go to your table 213, just like we did before, and you insert your design ranges, in this case for an SM12.5A. Insert those into that last column. The primary purpose here is just to be sure that you've got to double check for your target values against your design range. In this case, when you're doing your cold feed, your mix design or your job mix has already been set, so your target values are a set value. You're not trying to adjust anything. and you just insert those and you compare them against your design ranges to be sure that they meet those design ranges. Your next step is very similar to what we've done before. You're trying to determine how much of your screenings and then and your stone need to go into a specific cold feed adjustment. So now we go over to this case. We're going to do a trial and error. We're going to say 45% of your material goes from the screenings and 55% goes from the stone, and you insert that into your calculation worksheet. It's exactly the same thing as we did for the mix design. We take each one of those and we multiply those by that percentage that we just set as a decimal. So in the first case, let's say we have the 3/4 inch sieve. We had 100% passing the 3/4 inch sieve. We multiply that by 0.45, and obviously we get 45%. We skip on down to say the number 8 sieve. We have 100% passing the number 8 sieve as well. We multiply that by 0.45. We get 0.45 again, exactly what we did before. So skip down to the number 200 sieve. We had 12% passing the number 200 sieve, and multiply 12 times 0.5 and you get 5.4. So now let's skip over to the stone side or the coarse aggregate side. Let's say that on the second sieve or the 1/2 inch sieve, we have a 98% passing to that 1/2 inch sieve for the stone. We multiply that by the percentage of that blend, which is 55. So you multiply that by 0.45 and you get a percent blend of 53.9. We skip on down to the number 8 sieve. We had 9% passing the number 8 sieve for this material. We multiply that one by 0.45 and you'll see that we get a percent blend of 5. In this specific case, we didn't have any material passing the number 200 sieve, so we have 0% on the number 200 sieve for this stone. We do essentially the same thing as we've done before. We look at each one of those and we calculate a total blend. So looking at the number 4 sieve, if you total those two together, you total a 45 for the screenings and a 23.7 for the stone. Add those two together and you get 69. Same rule applies here. You round that to a whole number. You do that for each and every one of the sieves that you've got for this specific blend, and you calculate the total blend for each one. So we'll see that we have on the number 8 sieve, we have 45% of the blend on the screenings. We have 5% of the blend on the stone. That gave us a 50 for the total blend. Now we do the same thing as we did before, and we compare the total blend to the target value on each and every one of those sieves. So if we go down those sieves, we'll see that, say, on the 1/2 inch sieve, we had a target of 98. Our total blend achieved a 99, so we're very close there. Skipping on down to the number 4, we had a target value of 70. Our total blend achieved a 69, so we're right on top of the same target there. We had a target of 21 for the 30 sieve, and our total blend achieved a 20. And even on the 200, we were within 1 decimal point of meeting our target. So we had 5.4 for the total blend compared to a 5.5 target. So in this case, we'll try another solution. Let's go through this using a screenings of 60% versus 40%. If you recall, in our previous one, we had 45 to 55. Now let's try one at 40 and 60. So if you run all those numbers just like we did before, and you calculate the total blend for that same gradation with a different blend of 40 and 60, you'll see now that we've adjusted that such that we're not quite as close to our target as we were before. So if you look at, say, the number 4 sieve, the total blend was 66 and our target was 70. So we're a little bit off on this one. On the number 200 sieve, we're still pretty close. We had a total blend of 4.8 for a target of 5.5. So based on these two problems, if you look at it, clearly the 45 to 55 blend of screenings to stone produced a far better cold feed blend than the 40 versus 60% blend. Thank you very much.